Off with an introduction to Windows Phone 7. It's quite a new phone OS, so for those of you who aren't familiar with it, I just want to provide an overview. Then I'll talk about the security model, the security features, and then finally, perhaps the most interesting bit, the vulnerabilities. I won't be covering managed application security, cloud storage, or UIX native applications. Really, this talk focuses on the platform security, the OS level security offered by the platform. So Windows Phone 7 phones, currently there's multiple different OEMs. It's the same base operating system, but there's different handset manufacturers out there, the original equipment manufacturers. With that, it's the same base operating system by Microsoft across all of the OEM phones. However, the OEMs are allowed to make customizations to the base OS. They're allowed to write their own applications, device drivers, and so on to actually support the platform. This actually gives the OEMs an elevated level of access to the platform, which normal developers don't get. And then finally, well, it's a closed platform. You're not meant to be tinkering around with the operating system underneath. From the user's perspective, all they can do is really configure the settings which are exposed, but they can't make changes to the underlying OS. And this is entirely undocumented as well. So all this research is purely from a reverse engineering perspective. So the OS, well, the OS, it's based on Windows CE. It's somewhere between 6 and 7, I think, where the code base was forked and customizations were made for Windows Phone to support the new phone platform. All the phones on the market currently, they run ARM architecture CPUs with a 32-bit address space per process. So that gives you 4 GB virtual address space, which is divided into 2 GB for the kernel and 2 GB for the user land. And when you apply updates at the moment as well to Windows Phone 7, well, they're pushed out via the Windows Update service. They require you to tether your phone with Zune. There is support for over-the-air updates in future, but currently it's not implemented. All updates as well, of course, they need to be digitally code signed to actually execute on the device. So I think it's really important to understand the application model, how applications are developed for the platform and what functionality application developers get. So normal developers, which not the OEMs, they're restricted to writing managed code. They're restricted to writing C# on a customized Silverlight XNA framework. So that gives you the additional security of the .NET CLR, type safety, and so on. There's no actual native code allowed for third-party developers. It's a little different from the mobile operators and the OEMs. They're actually allowed to write native code for device drivers and so on. So that gives them an elevated level of access to the platform. There's also no side loading. You can't load applications directly to Windows Phone 7 phones unless they're developer unlocked. So for testing purposes, you can put applications on there if they're developer unlocked. But otherwise, all applications developed for the platform, they need to go via the marketplace. They go through a marketplace verification process. And if the verification process passes, then the code is signed and it's allowed to be deployed to the device. So the security features, well, there's a number of different subsystems which work together to really maintain the security of the phone. These systems work with this concept of this overall concept of a chamber-based security model. It's quite a novel idea where basically processes are sandboxed and restricted by the level of trust required on the device. So, for example, at the top of this model, you have the trusted computing base. The trusted computing base is where the kernel mode, device drivers, all security critical functionality actually is implemented in the trusted computing base. So as an attacker, to compromise the security fully, you really have to have your code executing in the trusted computing base. Then you have the elevated rights chamber. Elevated rights is for user mode device drivers, ones which aren't in the kernel. So drivers which need to provide globally accessible services across the device. And then below that you have the standard rights, which is for native code on the device, which doesn't need to provide globally accessible services, but still needs native code access to the device. And then finally, probably the most interesting chamber for developers and security professionals, because the first three are actually, they're fixed permission sets. The OS, the security policy in the OS basically controls what permissions processes which are executing in these different chambers have got. So the first three, the top three, are static permissions. The bottom one, the least privileged chamber, LPC, is basically, it's controlled by dynamic capabilities. So when you develop an application for Windows Phone 7, you specify what capabilities the application should have. These are things which are security critical or privacy critical functionality, such as access to the camera, access to the microphone, networking, and so on. And what these do are, when the application is deployed onto the device, then the capabilities are parsed and the chamber is provisioned with, the LPC chamber is provisioned with access to this additional functionality. But by default, the LPC chamber is really locked down, and you can't access any of this functionality without the capabilities. So this works together as well with the code signing model on the device. So binaries which are shipped in the ROM in the operating system at build time, they're implicitly trusted because they got built into the OS. But they still require these policy entries to actually execute on the device. Any of the binaries which you put on the phone after the ROM has been built, then these require to be code signed with a valid code signing certificate. So it means if you just put a binary on the phone, then it won't execute because A, it's not code signed, and B, there's no policy entry there specifically allowing it to execute on the phone. There is an exception to this, which is developer unlocked devices. For testing purposes, then they have the ability to run LPC unsigned code. So this actually maps to the certificate star on the device. So if you take a look at this sub-CA here, which is for the trusted computing base, so code which is signed with a certificate which chains to the TCB sub-CA is honored to load into the trusted computing base chamber. There's also one, so these map to the different chamber assignments from the chamber-based model I showed previously. And the bottom one is for the least privileged chamber, which is where when you submit your applications to the marketplace, then it will be signed with this code signing certificate authority. This is all controlled by policy files as well. So in the policy files, you have a hash fingerprint of the code signing certificate. And this basically states that if code is signed with a certificate which has got a SHA-1 hash fingerprint of that value, then it is authorized to have execute access into the, that's a Windows SID for the TCB chamber. So that's maybe similar to system on normal Windows. And then that authorizes that code to load into the TCB chamber if it's signed with that. So this is controlled in the kernel. There's a module in the kernel. This module, the loader verifier module, it controls all the authentication and authorization on the device. It's the centralized point, the centralized gatekeeper for security on the phone itself. So it uses the policy framework, policy entries, which I'll talk about in a second, to determine whether determine the authentication and authorization on the phone, and uses the code signing as well. There's two critical databases which are used by the loader verifier. The accountdb.vol, which is where the accounts, the usernames, groups, and so on, assignments are stored, and the policy database, which is where the policy entries and the security policy for the device is stored. This is obviously this is protected by the trusted computing base as well. It's in the kernel, so an attacker needs to bypass this or compromise this to actually have full control of the device. There's three functions which are used. Loader verifier authenticate file. That basically just checks that code is signed with a valid code signing certificate. If code's signed with a valid code signing certificate, then an authorization check is performed to ensure that the code is authorized to load from the caller chamber to the target chamber, the requested target chamber. And finally, you have the loader verifier provision security for application. This is called when a new application is installed to the phone. All the capabilities are parsed, the chamber is created, the user's group's assignment is performed, and policy entries are actually created to allow it to run. So this policy framework, which I keep referring to, this is a centralized security policy for the phone. There's just one security policy on the phone itself. It's basically it's controlled. It's XML based. So the modules, when you build the operating system, there's XML policy documents which they basically specify what security critical functionality should be exposed from that module on the phone. These policy XMLs, they're all combined into one big policy XML, and then finally it's compiled into this centralized policy database. This is for, I assume, for fast lookups on the device, so it doesn't impact the performance by performing all these authorization and authentication methods. And this, of course, is protected by the trusted computing base as well. So to compromise the security policy, you need to compromise the trusted computing base. Policy entries themselves, well, they work with these things called international resource identifiers. IRIs basically identify things like the registry, the file system, resources on the phone. It's quite granular. You can specify single resources, or you can specify wildcard matches. So everything, for example, under a registry subkey will be matched by these IRIs. These are used in the policy files. So this policy file basically states that the loader verifier for /windows/taskhost.exe. So that's the file system path on the phone of that binary. It basically states that that binary has execute access and load access to the target chamber SID. For that user account. And for every binary which is on the phone, there needs to be an associated policy entry stating what chamber it can execute in and what rights it has. So there's also when normally on Windows, you call create process to create a new process as well. But process creation is also protected by the security policy. One process can't spawn a new process by calling create process unless there's a security policy entry stating that it can. So in this example, the account, it basically states that the account can launch /Windows /cprog. So that's the phone dialer. It basically states that this is a capability for Internet Explorer, ID cap IE. It basically states that Internet Explorer can spawn the phone dialer from the browser itself, but any other calls to create a process from the web browser will be sandboxed and be restricted by the policy entries. And then, of course, as I mentioned, resources are protected by the policy entries as well. So any access, when a request is made to access the registry or the file system, then a policy decision needs to be made to determine whether this is actually going to succeed or not. So there's also a number of exploit mitigation techniques as well, which are built into Windows Phone 7. It uses address space layout randomization. So for those of you who aren't familiar with ASLR, it basically randomizes the memory address space of that process so that data is not at predictable locations. So for example, if an attacker injects their shellcode, then they won't know whereabouts it is in memory, where that buffer is stored, that kind of thing. And it just basically increases the difficulty for an attacker to perform an attack against the platform. It also has execute never. This is a non-executable memory protection. So if memory pages are marked as writable, then they won't be executable as well. And this is enforced by the hardware as well in the CPU. Yeah. So as an attacker, then that was basically it from the security model. I'm now going to speak about how to bypass this security model, how to perform attacks on the platform. There's a number of different stages which you need to go through to actually compromise the platform because of all these security protections. So the first thing I really wanted to do was to enable error reporting. There's no way at the moment to do any kind of debugging on the device. Kittle, all that kind of normal stuff for debugging has been stripped out of the device. So the only way, a fellow security researcher, KF, actually found a way of enabling crash reporting. That's, if you've ever seen Dr. Watson pop up in Windows when a process crashes, it's equivalent of that. It's a post-mortem crash dump. The problem is you've got 128K of information in these crash dumps. You have the registers, you have the stack frame, you have a few bytes around the instruction pointer, the program counter in this case, and makes it quite tricky to write an exploit just working from crash dumps and with this restricted amount of information. But yeah, there's another problem as well, is that even though crash dumps are enabled, even though you can enable crash dumping, you can't actually access the crash dumps because in your application you're restricted to the least privilege chamber. So the sandbox stops you from accessing the crash dumps. It's necessary to find a way of actually breaking out of the sandbox to access this file system path to get the crash dumps off the phone, so you can load them up in WinDBG, start looking at why a process crashed, and writing your exploit for it. So this involved abusing a capability, a totally undocumented capability given to the OEMs, to the handset manufacturers, called ID cap interop services. This isn't actually available in the public development SDK. You can use this functionality by using reflection, .NET reflection, and instantiating the objects on the phone, and then basically abusing this capability and OEM device drivers to access the file system. So at that stage, you've got crash dumping working, but you really want to you really want to be able to do static reverse engineering of the binaries to look at the assembly language code and find vulnerabilities in the assembly by reading it. So in order to do that, well, Windows C modules, they're not normal PE file formats. It basically requires combining the sections together, adding a PE header to there, and then when it's in the correct format, you can load the code section and so on up in IDA Pro, and you can start reverse engineering it and looking for vulnerabilities. So at this stage, you really want an initial vulnerability, some way to get code execution on the phone. So you might find a vulnerability, for example, in the web browser. But even if you gain control of the program counter, then the instruction pointer, the instruction which is going to be next executed, then the problem is that you still have to bypass the ASLR and non-executable memory protection as well, because you don't know where your data is in memory because of the ASLR. You also, even if you could find your data, your shellcode which you injected, then you still wouldn't be able to execute it because the memory page would be marked as non-executable. So you need a vulnerability to actually to get around that. Unfortunately, that vulnerability is not patched at the moment by Microsoft, so I can't disclose the ASLR XN vulnerability at the moment. But as soon as that's fixed, then I'll publish an advisory on that. So at that point, you've gained a code execution in the least privileged chamber. But the least privileged chamber is not that great because you're basically restricted to what the functionality which the application you exploited has, its sandbox. You really want to break out of that sandbox and access the sensitive information on the phone. So outside of the sandbox, well, you have the things like the SMS database, the sensitive information. So you need some kind of privilege escalation as well to break out of the sandbox and give you either TCP or elevated access to the device. So just a little detail here. I had a feeling that that the OEMs were introducing vulnerabilities on the platform because of for two reasons really. One, that they have elevated access to the platform, and secondly, that we'd performed other research on Android, for example, where the OEMs had introduced vulnerabilities on the platform for their handsets. So on Android, we discovered that there was HTC had implemented this install permission on their web browser for some reason. I think to do flash updates, but it's basically a case of bypassing the security model to provide additional functionality, but it weakens the security model on the device. There's also the case of a sound recorder, HTC implementing their own sound recorder. Now on Android, I think that you need a permission to actually access sound recording functionality. It's a security critical thing. But HTC had implemented their own sound recorder, which you could just, if you had a malicious application on the Android, then that could just record sound using this and using its RPC endpoints. And then finally, the HTC logger as well. This has made the news recently where they've been tracking quite a large amount of information from the end user, privacy critical information. So I thought about applying this to Windows Phone 7 to see what OEM vulnerabilities were actually introduced. So I really wanted to start off by looking at a way if I could fingerprint the devices to determine what OEM, what handset they actually were. And then that way you could deploy a device-specific payload. It wouldn't require writing an exploit to target all the different devices. Depending on what device you fingerprint, then you can deploy a payload for that device. The way I thought about doing this was, it turns out that the user agent the user agent actually exposes what the device is. So this one, for example, is a HTC HD7. This one is a Samsung Omnia. So it means an attacker can perform more targeted attacks against users of these devices. For some reason, it also discloses that it's running ARM architecture, which is kind of handy. So I exploited a web browser vulnerability to gain initial code execution on the device. So here you can see the program counter set as 0C, 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 just as a value to demonstrate control of this. But then after this, you really need to bypass the ASLR, the non-executable memory protection, to get your initial code execution. As I mentioned, then that's unpatched at the moment, so can't talk about that. Sure. Yeah, so that's the crash dump which I took off the device and transferred it to my PC. So I used because there's no socket support either in Windows Phone 7, normal socket support. But you can do yeah. Yeah. Yeah, yeah. This research as well was performed before Mango. So this is like Nodo and so on. But yeah, in my case, I used HTTP to just transfer the crash dumps from the device. I posted them back to my web server, and then once I downloaded them from there, and then using that, you can load them up on WinDBG on a normal desktop PC and start looking at these dumps. So that'll give you these dumps. But as mentioned as well, these are context dumps. So you've got no access to any of the information in the heap. In most of the memory pages, you've got 128 kilobytes in this dump. So you've got the registers, the stack frame. It's quite tricky to write an exploit with just the registers and the stack frame and where it crashed. And sometimes you don't even have where it crashed as well. Yeah. So the OEM capabilities, I started examining what OEMs were given, and they had this specific capability called ID cap interrupt services. It's used for normal applications to access device drivers and additional services on the device. It's totally undocumented. In the public SDK, there's no code for this, but you can use reflection, or you can take the assemblies off the phone and use those, link against those, and then call that functionality. So this is just a case of really instantiating the right objects, using the COM bridge, and then and creating this manifest file, the WP interrupt manifest, in the archive. This allows you to write native code. So I started examining the device drivers which were implemented on my HD7 phone. Turns out that Samsung had implemented a device driver which gives you arbitrary read and arbitrary write access to the entire memory space of a process. That includes the kernel memory space as well. So you remember the kernel, the trusted computing base is in the kernel. So if you've got arbitrary read and arbitrary write access of kernel memory, then there's a high chance that you can get code execution in the context of the kernel as well and bypass the protections implemented in the trusted computing base. So the way I did it was to, So this is just a case of opening up a device handle to the device driver and creating the struct in the, hopefully you can see that, creating the struct with the mode, read or write access, specifying the address, and specifying what you want to write at that address, and then calling the device I/O control, and then that allows you to do 4-byte writes anywhere in the memory space, which is quite nice. So I thought, how can you turn arbitrary read and write access into code execution in the context of the kernel? On Windows, you have, on normal Win32, you have the PEB, There's a similar structure on Windows CE. It's called the K data struct, and it's at a fixed memory address in every process. So this is quite an old school method. You can basically patch system call handlers so they point at an attacker controlled bit of code. And then when the system call is made, then the code will be executed in the context of the kernel, and your privilege escalation will succeed. So this was just a case of using the arbitrary read method to dump out data in this K data struct, locate the necessary function pointers, the pointers to the system call table, and and then patch those pointers. These are implemented using API sets as well. So it's just a case of patching the function pointers and detouring them to the attacker-controlled shellcode. Then you have code execution. I need to speed up a bit. So I was wondering whether these vulnerabilities were just limited to HD7 devices. It turns out that Samsung had implemented a bit of functionality themselves for device provisioning of the devices, allowing them to make configuration changes to the device. So I audited the binaries for the Samsung as well. I located a directory traversal in one of the Samsung binaries, which it's meant to read device provisioning XML, but the problem is you haven't got write access to this directory. The sandbox prevents you from having access to this directory. So you need to be able to write to the so you can use the directory traversal vulnerability to write to a directory which you have control of. So this is a case of constructing a path to a directory you have write access to, and writing the XML. Problem is you can't create new processes because of the policy restrictions. Turns out Samsung had actually implemented a device driver to create new processes. Yeah. So in this case, what you do, well, you want to extract sensitive information, eavesdrop, rootkit, for example. Maybe disable the policies or certificate checking. If you're a malware writer, maybe you want your application deployed later. Wouldn't it be nice if there was code there to get around this? Policy faker and certificate faker? That doesn't sound like legitimate functionality to me. License faker? DRM, anyone? Backdoor fixing developer unlock to enable state. Backdoor? Yeah. It's a bit weird. And you'll notice that these functions have the same names as the actual legitimate functions controlling the loader verifier. So I'll just do a quick demo. Okay, so this is me loading the web browser up, going to a page which has got exploit me on a link, which is my malicious web server. The web server at the top is delivering the exploit payload. On the bottom, there's an exploit handler there, and the exploit handler will receive a file from the phone when the payload executes, and get transferred back to the attacker over the Wi-Fi link. And in a second, you should see this occurring. And now we have the browser history transferred back to the attacker. Thank you. So Mango, well, Mango's the latest version. It restricts the method I use to debug and develop the exploits. But ultimately, the design still allows the OEMs to implement these security, risky functionality. So it's really up to Microsoft to make sure that the OEM's code is at the same code quality as the base operating system. My conclusions on this really, It's a strong granular security model. It's clear that a lot of thought has been put into this security model. It requires an attacker to go through multiple different stages before they can exploit the platform. It also shows that an attacker needs multiple vulnerabilities and exploit mitigation bypasses to attack the platform. Shows that an attacker can use OEM vulnerabilities. If they specifically want to target a handset, they can go for the lowest hanging fruit. They don't need to go for Microsoft's code base. They can go for OEM's code if it's of a lesser code quality standard. That's it. Are there any questions?